So once again, schedule. Recitation on Monday will be all about the ecosystem. FabX global event, Fab Foundation, Fab City programs across the network. Then we're in the 2-week midterm break. Once again, recapping, meet with your local and global instructor, review your weekly assignments and your final project. And then this is a challenging and exciting stretch, which is why we expanded into this midterm stretch. You're going to make a machine. This week's assignment is a group assignment. Until now, you've been doing separate assignments. This time, you're going to work together on a machine. It can be multiple machines in one lab. It can be one machine per lab with multiple tasks. And you can collaborate across labs on the machines. This is really at the heart of the class. One of the main goals of Fab Labs is to obsolete them technically, initially by, instead of having to come to the lab to get to the machine, we want you to go to the lab to make a machine, so a lab can make a lab. And that's really progressed very far. Excuse me. As a reminder, lots of cameras are off. Again, I have to keep reminding you, once we're in class, your cameras need to be on. So I'm going to cover 2 topics today. The first is the mechanisms, the mechanical part, and then the second is the machine part, the automation of it. Let's see, let's look ahead just to let's see, I'll come to lots of examples, so let me not do that yet. Okay, so this first part of the class is the passive part, just the mechanism. And then so a machine is defined for this sequence as a mechanism, things that move, actuation, something that makes it move, automation, control of what's making it move, and an application. And so a fun example that I've linked here of a really interesting mechanism, excuse me, is this project from the Kerala lab, which was this just gorgeous clock that works by having a degree of freedom mechanically moving each suspended hand. And so it's a beautiful example of an interesting mechanism. So first, vendors. I'm going to give you a lot of examples from McMaster Carr. I don't necessarily recommend that as the most convenient source to buy it. It's very well documented. Stock Drive Products is a good industrial supplier. Amazon has bought up a lot of vendors. And so now through Amazon, there are a number of industrial suppliers you can purchase through them. And then Masumi is another really good one. All of the things I'm going to talk about the mechanisms, they're a good vendor for those components. Some general principles. So a material is characterized by a stress-strain curve. The way you remember it is stress sounds like press. That's what you do. Strain sounds like pain. That's your response. So you apply stress and strain is the response. And so a linear relationship is like a spring. You push on it, and the harder you push, the further it moves. A typical material starts linear, it goes nonlinear, then you get into so in the linear regime, it retraces. Eventually, you get plastic flow where it creeps. Let's see, Rico is asking also about Taobao for parts. Yeah, there are a number of vendors globally. I'm mentioning in particular the ones I'm linking to. Um, so let's see, I'll add a link for that. Uh, Eventually, when you push the material far enough, you get plastic creep. And then at that point, it's hysteretic. It doesn't repeat because you've actually deformed the material. And then eventually you get to a limit where it fails. And that limit is the strength of the material. The slope of this line is the stiffness. Where it fails is the strength. And the area under here is the toughness of the material. As you build machines, this is a beautiful paper from the 1800s from James Clerk Maxwell, who's famous for electromagnetic fields. And what he points out there is a structure has constraints and degrees of freedom. So, and I've mentioned this before, it came up before, but I'll say it again here. If you make a bookshelf like that, it'll wobble because if it shears, everything is the same length, but there's no constraint. But if you cross brace it like this, you've added extra constraints and it won't move. So as you build a machine, you need to keep track of what are the constraints and then what are the degrees of freedom. So the machine can move it in the degrees of freedom you want it to, but it's constrained in the degrees of freedom you don't want it to. A big topic for today is going to be hysteresis and backlash. So if you have, if these are threads, Narella, hand raised? No, okay. If you have a nut on the thread, there's a little gap here. And what that means is when you turn it in one direction, and then you turn it in the other direction, it's not exactly in the same position because the gap goes forwards and backwards. And I'll talk about ways to reduce the hysteresis. Another important just background concept for today is force loops. And I've mentioned it before, but I'll say again, if we're making a milling machine, here say is our cutting tool. That's going to go in a collet, that's going to go into a spindle, that's going to go into an axis. And then all of that goes on a horizontal stage that goes onto a vertical stage. And then we have a bed, and then we have our stock, and we have our fixturing. And the positioning between here and here, which is what we care about, actually is a function of the error stack up at all of these positions. So to design the machine to make this tolerance tight, we need to understand the errors in the whole force loop. And in particular, we want to minimize the force loop to minimize that error stack up. A really handy concept is a kinematic coupling. And these are surprisingly subtle. So this image just looks like some balls and slots, but that lets you actually position something to micron accuracy. So what's going on there is let's see. Let me start a new page. If you take one slot and one of those spherical balls, it's free to move anywhere on that line, but it can't move transverse. But then if you make three of those, each of those is constrained along a line. And so it means the total structure can only go in one position. So if you just slap this down, it seems like coarse positioning, but there's only one solution for where each ball goes that registers it. And so it lets you take two parts and align them to very tight tolerances. And then a final note, we'll talk about both accuracy and precision. So if this is a bullseye and we're shooting arrows, if the arrows go all over the place but they're centered, it's very accurate, but it's not precise. If the arrows go to all in one place but they're not centered, it's precise but not accurate. And so we'll talk about both of those. So those are just some background terms. Now, for materials for machine building, you can use plastic. One of the materials we like to use is high density polyethylene, and I'll show you that. We use metal parts, and I'll talk. Oh, my three. We need to name that. Yeah, Hank is noting the trade war. The trade war is horrible. I apologize on behalf of that. It really drives the value of being able to sustainably produce locally. We're going to use metal parts, in particular metal extrusions I'll be talking about. We'll have, in some places, we'll use rubber or foams to damp energy. Garolite is a really interesting material for machine building. It's the PCB stock. And carbon fiber is hazardous to machine, but garolite is friendly to machine. And in particular, you can get thicker garolite sheets. That's a nice material, easily machined for machine building. Wood gets used. In general, I don't recommend wood because it'll swell and deform with temperature and moisture. Cement is a really interesting option for machine building. We care a lot about stiffness, and often we care about mass. And so one way to build machines is instead of cutting to cast, to make a mold and cast the machine parts. And we'll see some examples of that. And then to make the hardest parts, we use ceramics. And in particular, I'm going to talk about that in molding and casting. There are ceramic precursors you can mold, fire, and make custom ceramic parts. Adhesives, we tend to stay away from. You can use adhesives to glue things together. A good place, for example, is acrylic. Acrylic glues actually melt the acrylic, and it's as strong as the underlying acrylic. But in general, we stay away from adhesives because it's hard to undo them. And so we want materials that we can disassemble the machine, revise it, and reassemble it. We're going to have lots of fasteners, so nuts and bolts, and it's a surprisingly subtle, interesting subject for all of the types of nuts and bolts. So let's see, I don't know why that's not loading. Oh, I'm connecting. I'm connecting through a proxy server. Okay. So just within the humble subject of nuts, there's a huge range of types of nuts and bolts. So one of the main, so you can use a nut to tighten. Um, uh, if you just tighten a nut and the machine vibrates, it's going to move. It'll eventually loosen. So one of the ways to deal with that is to use lock washers. So a plane washer spreads out the load from the nut, so it doesn't deform the material. A lock washer adds a little bit of springiness that loads the nut and prevents it from walking. Um, and a lock nut, in particular, is a nut that has a little bit of elastomer in it. So when you tighten the nut, again, it keeps it from walking. And so washers and nuts, you don't obviously need right away, but if you leave them off, for example, without the washer, you might plastically deform the material. Without the lock nut or the lock washer, your structure will start to loosen. So they're very just important for the life cycle of the machine. Um, oh, I don't know why the server link is not stable. Heat set inserts are a handy thing if you want to have threads in a 3D print. They're threads, and you actually poke it with a soldering iron and you just melt it in, and it lets you screw into a 3D printed part that would otherwise deform. Rivets are surprisingly useful. You can get manual rivet guns and pneumatic guns, and they let you quickly pop a structure. So many kinds of airplanes are held together with uh, rivets, and then these sort of pins are important that can keep parts from walking out and constrain their range of travel. So that's just picking fasteners. Then we need to make the frame of a machine, and so a classic machine. Um, I'm going to talk about for a few different reasons is here's a uh, XY motion system. This is using a extrusion. So extrusions have come way down in cost from the vendors I mentioned. You can actually even have for a few $1,000s have custom extrusions made. And so these are stiff. You can slide nuts in them to bolt them together, and then you can quickly make frames of machines, and you can get extrusions in all sorts of sizes and shapes for the loads. So that's one of the most common ways we frame the machine is with extrusions. You can get plastic extrusions. Then T-slot is what we call these T-shaped slots. And so there's a whole family of fittings where you have captive nuts that slide in the slot, bolts that go into it, and then framing pieces like corner brackets, anal brackets, wheels, are all parts of kits that go into the framing. And then finally, a different approach is this is Nadia and Jonathan, two machine builders. And this is self-aligning. Oh yeah, in the chat, there's a 20-minute video on washers. It's a surprisingly interesting and subtle subject. This is a self-aligned joint. So rather than bolting together a frame, this was machined in HDPE, high density polyethylene. And then if you look at this joint, when you snap it together, the tab centers it. These side beams latch it in. These posts constrain it from rocking. And so just the act of clicking it in takes up all, it's reversible. You can take it back out again, but it takes up all the degrees of freedom. And so by just snapping it together, you align all the parts of the machine. And so that's a self-aligned framing. So those are all parts to build the frame of our machine. Then the most important thing to come is drives are, we're going to have actuators, motors of various kinds, and solenoids, and we have to transfer the forces from them to the machine. So gears are, again, a surprisingly beautiful, subtle, interesting subject. So here are all kinds of gears. The most common gear is involute. This is a mod's workflow to design an involute gear. And if you look at the involute gear, the gear is not just teeth like that. The problem with teeth like that is if you mate to it, one whole face touches and then disconnects, and you get very jerky motion. Instead, if you look at the involute gear, it has this slightly curvy shape. And if you look carefully, you'll see it's touching in just one place. And so as you turn the gear, what the involute does beautifully is it rolls. So there's only one point of contact. And so you get smoother transfer. So involute gears are the most common gear. And if you make your own gear, you use a gear generator to get the shape of it. But there are many other gear shapes beyond involute. Jens's, who I'll talk about, he makes his own gears, and this rack and pinion we'll talk about in just a moment. This is a cycloidal gear, which is designed with a spherical rolling shape. A cycloidal gear has more space to get into it to make the rack and pinion. So for fabrication, it's preferred. It's less efficient at force transfer. The force angle that it transfers, the angle of the transfer is steeper, that puts more load on it. So these can be smoother, they can be easier to make. They're less effective for the force transfer. So far I've just done an extruded gear that has continuous transfer on one point, but it's extended. In a helical gear, it's doing that in 2 degrees of freedom. As you roll, there's one point of transfer in the axial direction, but there's also a single point of contact in the transfer direction that moves along the helical gear. And so a helical gear gives you quieter, smoother rotation. And then the logo of a Citroën car comes from the use of this sort of gear that's herringbone. The helical gear has nothing that constrains the gear against holding it from lateral motion. That has to be external. The herringbone has those back-to-back that self-aligns the gears, so you get smooth and self-aligned motion. And that was part of the transmission of the Citroën. That's where their logo comes from. So all of that goes into just picking a gear. Then often you need to change when we talk about motors, there's an RPM the motor is happy with that can be very different from the motion you want. So let's see, a planetary gear looks like a sun with planets around it that rotate. And so that's a common solution to take something that's spinning quickly and reduce it down for something that wants to spin more slowly. And a really interesting, non-obvious way to do that is a harmonic gear. What this does is there's an outer tooth that's rigid, there's an inner that's deformable, that's flexible, and then there's this elliptical drive. And so at any one point, the inner and outer merge, but crucially, the inner and the outer differ by as little as one tooth. So as the deformable inner moves with the elliptical drive, when it comes all the way around again, because they have a different number of tooth, the alignment can change by one tooth. So when you look at a robot, like a robot arm or a robot dog, this is the most common thing used in the shoulder of the robot. It lets a motor spin at a higher RPM where it's efficient, but smoothly and slowly move the joint. Okay, so that's a harmonic drive. A rack and pinion is the pinion is the little gear and the rack is the linear gear. And so if we go back to this image of Jens's machine, he makes his own rack and pinion. So he machines this rack, and then on the motor he puts the pinion, and then that can run for as long as you want for the length of the rack. So you don't need you can buy it, but you can make your own rack, and then with the pinion it'll run as long as you make the rack. Common is a lead screw. So this is a thread, and when you turn the thread, a nut will move, but a garden variety nut will have backlash. So better than that is this is an Acme nut that's spring loaded, and the spring loading takes up the slop from the backlash. And so this is very common for you turn the screw and then let's see, uh, it, if you look at not all, but many 3D printers, that's what's going on here, that you have a lead screw, and then there's an anti-backlash nut. Now, the anti-backlash nut does have a fair amount of friction, so even better than lead screws is ball screws. And this looks similar, but it has recirculating ball bearings. And the recirculating ball bearings in the lead screw reduce the rolling resistance and make for smoother motion. And so a common way to drive linear motion with substantial forces is to use a lead screw with let's see, coming back to here, the lead screw with the ball nut. And that's used, you can get those up to very large diameters that can transfer very large forces. So you'll see that in machines that are working against forces. So those are lead screws, ball screws. This is a little funny, quirky offshoot. This is a threadless linear drive. It's three heads on a hardened rail, and it's a little bit like the kinematic coupling. There's only one stable position, and so as you turn the hardened rail, the threadless will drive along it, and the attraction of that is smooth motion. Then for large forces, you can use chains, but the chain, the force is very uneven. So a lot of use gets made in machine building of belts. And so these belts look like a floppy rubber belt, but they're internally reinforced. So you can't stretch it. The space between the teeth is controlled, but you can bend it. And so you route these timing belts around pulleys that they made on and use that to distribute forces in the machine. And then a neat way that I like for machine building is this looks like a metal thread. It's kind of like the inside of an electrical wire. And it's designed to be bendy but stiff. You can't stretch it at all. And so coming back to this example, what's going on here is what's called a capstan drive. So if we come down to here, this is somewhat subtle. So this is that wire thread. You can use any thread, and then there's like fishing line that's less stretchy, and this is less stretchy still. Here's the motor, and you see this idler, the second pulley. It's doing two different things. One is if you just wrapped the thread around the motor, as the motor turns, it would move up and down. Here, if you look at this wrapping pattern, as the motor turns, they kind of cancel each other, so the position of the thread doesn't change, which is one thing you want for the machine. Then the second is this is tensioned. So he talks through, you pull the thread, and then you move a transverse loading element, and it pulls tension in it. And the second thing the idler is doing is increasing the friction. So with the timing belt, the teeth mate, which is good. It can be a little bit less smooth from the teeth successively mating, and you need gears that match the pitch of the pulley. And it's harder to cut and join the timing belt. With the thread, you can make it whatever shape you want and just unroll it from a spool of it. But it could slide on the drive motor. And so the wrapping under tension around the idler significantly increases the friction, so much so that then when you made the machine, you can't just by hand displace it. It's constrained almost as tightly as the timing belt would. And so these sort of capstan drives are a really good approach for force transmission, because this could be any shape you want. It could be linear or rotary, it could be long or short, and you just wrap the filament for whatever shape you want for the machine. Okay, so all of those get our forces to where we want to go to. To guide it, a common use is guide shafts, where these are hardened rods that you can slide along. You can get guide rails that are linear bearings that go on a shaft. And at lower cost, you can get slides that when you don't need precision, when you just need to move something, you can get these slides. Then we need to couple our motor. And if there's much force on it, it's a problem if there's any misalignment between our motor. And so what these do, so a U-joint lets you drive at an angle, but there's a lot of friction with it. What these couplers do is they can flex a little bit in angle, but they're really stiff when you rotate. So when you assemble the machine, even if there's a little misalignment between the motor and the shaft, you get smooth power transmission to it. Then we need bearings, because things are going to be moving. And if you just rub surfaces, there's a lot of friction. So there's many, many, many kinds of bearings. So most common is a rotary ball bearing like that. And in a minute, I'll show you other kinds of those. Those are rotary. a thrust bearing handles a normal force rather than a rotary force. A linear bearing is what I showed you a moment ago. When you want to have something move along a straight line, you use a linear bearing on a rail. If the forces, let's see, the turntables are when you need to rotate a load. Sleeve bearings are if the forces aren't too long. Instead of a ball bearing, these are permanently lubricated, and there's some friction over their time, not as smooth. But if the forces aren't large, they're cheap and easy to use. A sleeve bearing, yeah. Uh, Oops. So for some reason, boy, I don't know why that is. Um, a pillow block is where you slide surfaces together. Again, we don't use that for large forces. And then one of the really exciting thing that's happened, thanks to the combination of our friends in Shenzhen and skateboards and rollerblades, is the kind of bearings you can use for skateboards and rollerblades. Jacob, a thrust bearing is for a normal force. So, like when you have a turbine in a hydro plant and that weighs 20 tons, the thrust bearing is what holds up the turbine. These sort of bearings have come way down in cost. So they're colloquially called skateboard bearings, but they're used for many other things. So these are rotary bearings that are down to like $1 each. Now you need to be a little bit cautious because the quality of them varies very significantly. Other just note is generally you want to get sealed ones that are lubricated internally, but they're sealed so you never need to re-lubricate them. And these have brought the cost way down. And so we use them all over the place. And then a final note is with bearings, you'll see a concept of preload. So the bearing, there's a little bit of a degree of freedom between the balls and the slots that lets you move the bearing along the axis by just a little bit. That can give it noise or rattling. So generally a good design principle is to have a little bit of an axial load on the bearing that makes sure the balls are always in good contact and it doesn't rattle. So you start with a little extra load that's built into the machine design. Then let's see, let's see, I should add a link. Yeah, I'll add a link to the following. So you can get the bearings in a wheel. One kind has a V groove, and one kind has a tapered wheel. Um, let's see. No, that's not what I'm looking for. So if we go back to Quentin's page. So for this mechanism I showed you, let's go back to here. So here's the mechanism moving. And if we look at the way he's routing it, this is a V-wheel where he's getting the bearing and it comes mounted in a hardened plastic that he's using to route the filament. And then for the carriage, if we come up to here, he's using now instead of the V, This is the tapered reel I was looking for, and then the tapered reel fits into the extrusion. You can get special extrusions that have angled faces specifically for this. If you use just a linear extrusion, there's a little bit more friction on the bearing, so the wheel will wear a little bit faster. It depends on how much load there is in the machine. But now pulling all these parts together in this machine, there's one more part I'll explain when I get to Core XY. But what he's doing is the framing is the extrusions. The power transmission is through the capstan drive. And then he's using V wheels to route the wire thread. And then he's using taper wheels to make carriages that guide into the slots of the extrusion. And all those come together to make the machine. Um, uh, Important for the life of your machine is you don't want the wires to get tangled. So cable ties and hook and loop fasteners you can use to tie it together. And then very useful are these carriers you can then use to bundle all your leads together so they don't get snagged. And then finally, mechanisms are how you use all of this. So this was a thesis I've shown you before on flexures. This was a instructor project making a flexural stage that we did in an instructor boot camp to move. And then the open flexure is using flexures to make all 3D printed microscopes. These have smooth motion, typically for limited travel. Series elastic is rather than driving something with force, if you have a spring between the motor and what you're driving, rather than specifying position, you specify force. And that's commonly used, for example, to make robots move more smoothly. Your muscles don't specify the angle of your leg, they specify the force on the leg, and that leads to smoother motion. Linkages are all the ways you get forces from somewhere to somewhere. And there's just a spectacular range of these over centuries. So these are all different ways of turning one kind of motion into another kind of motion. So many kinds of linkages. Uh, Movements then add belts and drives. And here's a whole catalog, again, of huge range of movements. Whippletree are used, you'll see these in horses. What these let you do is add varying forces to a structure. Pantograph lets you make a small motion control a big motion, or a big motion control a small motion. These are some notable mechanisms. Delta bots are 3 linear motions, and then when you link them, you can go anywhere in 3D space. Those are used often in large volume 3D printers. Hexapod goes beyond that to add 6 linear actuators, and then you can move anywhere. You can move X, Y, Z, as well as tilt angle. And then Core XY was invented by a former student, Alon Moyer. And it's Core XY is what's being used in this video I keep showing. But each shows a different aspect. So if you look now, if we come back to here, the stage is moving in 2D, but the motors aren't moving. The obvious thing to do is have a motor move one axis and then put a motor on another axis, but you're moving the mass of the motor and the wires to the motor. Here, you'll see, if you look at this interesting weaving pattern, the belt goes through that weaving pattern in both directions. And if you turn both motors the same way, the stage moves in X. If you turn the motors in the opposite direction, the stage moves in Y. And so this lets you move a stage without having to move the wires or the motors. And this is used in particular when you want to minimize the moving mass to move things very quickly. So that's Core XY. Saurus is a neat idea. This is a machine that just looks like folded sheets, and that's what it is. A folded sheet is floppy in the angle, but if you put three of them back to back, it turns into a linear stage that works by folding and unfolding the sheets. And so that's another kind of linear motion. Hang Printer is a neat project that takes all of these together to move a printer anywhere in 3D space. And you'll see all of these extra filament lines. What those are doing is going back to the Maxwell criterion, they're taking up degrees of freedom in the structure so it doesn't vibrate. Chuck Hoberman, a colleague at Harvard, is the guru of mechanisms. He designs these massive stadium-sized mechanisms, both for art and also for function. Massive structures that open, close, and move. So he's one of the gods of mechanism design. Another god is Theo Jansen, who makes the strand beasts, which are these lifelike creatures. This is completely wind powered, as just mechanisms as art. So that's a tour through types of mechanisms. And so the first part of your assignment is design the mechanism for your machine. You could make a milling machine or 3D printer. You could make a sushi slicer. We've had ketchup dispensers. What I want you to do is first design the mechanical parts, and in particular, operate it manually. Before you connect motors, it's very important you feel how it moves, and you can learn a lot by you being the motor, which works up to reasonably large machines before you connect the motors to it. And so you're going to document the group project, but on your individual page, document what you did individually. Now we get to the actuation. So let's go through stages. This machine Nadia made is just a machine. It can only do what it does. What Nadia later did is made modular machines. So this is a machine where she made modules that are separate linear axes, and she needed a hot wire cutter. And so she put together a few axes and a heater. That led to her doing a thesis on the idea of object-oriented hardware. Oh, good. This is the video I was looking for. Okay. So using that a few years ago, in Fab Academy, we had everybody make these. And I'll cover other options to make it. But to illustrate machine building now, this was a calligraphy machine. This was a 3D scanning machine. This was a coffee stirring machine, a marble light show machine, a hot wire cutting machine. Let's see, a painting machine, drawing. Let's see, another hot wire cutter, a lathe, This is a ketchup dispenser. This is a drink mixer. So this gives you a feeling for the range of machines you can do. We've already covered sensors and actuators in input and output week. End effectors are what goes on the end of the machine. So this is Nadia and this is Alan who invented Core XY. This is a machine they made in a briefcase. And then what they're going to do here is right there is a kinematic coupling, those three balls. And they have interchangeable heads. So one is a 3D printer head, one is a vinyl cutter head, one is a milling machine head. By snapping it into place, the kinematic mount aligns it so the machine knows where it is. And then they made a machine that can print or cut or mill as just a modular machine kit. So, and there's the motion system, and then the end effector is the thing that does something. For power electronics, we covered power transistors in output devices. And in the inventory, we have larger transistors if you're going to drive bigger motors, as well as smaller ones. In networking, last week we covered real-time networks, and I'm going to talk about that in a minute for the machine control. Once you have the machine, you need to make the path of what it's going to do. And here, this is a big milling machine in my shop. It's completely rigid. So for the path, you just tell it where the head goes. It's very different from this machine. This is a water jet machine. The jet is, when it machines, the head is moving. There's a jet of water coming out that bends. And so where it hits is not where the head is, but where the head was. So for a machine like that, the path is dynamic, not static. Part of using it is you need to pick a path that anticipates how the machine is moving. So next is, let's see, those links looks like I need to fix. So for the ShopBot, here are two kinds. This one is 23,000, this one is 30,000. The difference between those is open versus closed loop. So the open loop one, you tell the motor how many steps to make, and then you hope it did that. And if there's too much load, the motor will miss steps and not realign. The closed loop ShopBot has, in addition to the motor, there's a rotary encoder, and it measures the angle of the motor. So rather than trusting it did the right thing, you control it and you use feedback. And so, if you overload the machine, it might not move as quickly, but it'll still get to the right place. Now, in that case, it costs $7,000 to go from open to closed loop. But we've covered how to measure angle, how to do feedback. And so you can make closed loop systems now much cheaper than it used to be commercially. But that leads us to control theory. So this is another big subject for this week. So let's say we have a linear carriage, and we can move our motor. And we have a really nice system. So we have position feedback. So we even know where it is. And let's say you want to start from here and get to there. So the obvious thing you can do is turn on the motor, keep it moving, and when you get to your destination, turn it off. That's a terrible idea. And it's a terrible idea because when you turn it on, there's a big acceleration lurch. You don't drive your car by slamming it to the gas instantly. Usually you don't. Then when you get to the end, two bad things happen. If you suddenly stop, there's a big lurch when you stop, and you might overshoot. So when you're driving the car and the light turns red, you start slowing down long before you get to the where you're going to stop. So bang bang control is where you just turn it on and off. In general, that's a bad idea. PID is proportional integral derivative. This is more common. In PID, proportional is an error term that measures your deviation from where you want to be. I is an integral term that integrates up the baseline to get there. And D is a derivative term that penalizes you from moving too quickly. So PID is used very commonly, but increasingly, what's better than that is what's called model predictive control, where when you slow your car down for a stop sign, your brain is doing model predictive control. You have a mental model of how your car deaccelerates, and you're using that to figure out in advance of the stop sign when to start slowing down. And so to do that, you need to have a model of the machine, and then the controller uses the model of the machine to predict what's going to happen in the future and figure out what you need to do in the present. And this is a link to just an example of using all of that to balance an inverted pendulum. Let's see, Ferdy, that's correct. Ted, the founder of ShopBot, was a neuroscientist, and for fun in his garage, he made machines and discovered he was more excited by the machines than the neuroscience. Yeah, and that's a reminder that in this recitation, we had the machine builders come talk about all of their machines in the video from that. Okay, so that's control theory. Then the next thing you need to do is we have multiple machines. Yeah, Jacob, PID is much easier, but increasingly model predictive control. MPC is hard if you have to build the model from scratch. But in the era of maturing machine learning, it's become much easier to train models. So you can take a machine learning network and you can train a model on your machine to learn model predictive control. And then it's easier just to throw that at it. And so increasingly, it does make sense to train a really simple little network model to control even a linear axis. Now, all of this depends on how much torque the motor has and how fast you want to move. A simple drawing machine, there's so little mass, you could ignore all of this. As the inertia of the machine increases, this becomes more important. So
Neil,
now, yep.
what goes into the model, like itself? What characteristics of the
So
machine would you want? I mean, I
there's
know inertia would be one of them, but is
yeah,
there?
um, yeah. So again, there's two ways to do model predictive control. One is from first principles. You actually simulate a physical model of the system. The other is purely experimental. But the in particular thing is, um, you know, if we take this example, if we have the position versus time as you move the machine, PID uses the integral and derivative, which means you want to know where you are at more than one time step. In a typical model predictive control, in an empirical one, you take a window of some number of past samples of what the machine is doing. And then you use all of that to predict what it's going to do next. And predicting what it's doing next is its position, velocity, and acceleration. And then you train a model that takes the past history and predicts the future of the machine. And then you use that model to feed back on how you provide the signals into it. So you can start from physical, or you can just start from an empirical one and train on it.
Thank you.
Okay. So then we now have, well, let's see, if we just start already with the core XY, in the core XY, we have two motors, and then we have our core XY. But then we might have a core XYZ where there's another motor controlling the Z axis. And then we have an end effector that might be a spindle. So we've got multiple degrees of freedom and we need to coordinate them. The standard way to do it is we send all of these back to a single controller. And I'll show you examples of that. That's easy because this controller can talk to everything. What's bad about this is, let's say you wanted to add one more degree of freedom to the machine. You can't if you run out of ports on the controller. Or let's say if you wanted to change the design of the axis, you have to get back in and you have to change the code in the controller. So the alternative way to do this is to take all the degrees of freedom in the machine and just put them on a network like we covered last week. And so you don't have a controller in the machine at all. So all a motor knows how to do is make a step, but you network the machine, and then in software, you use the network to tell it what to do. And so in that case, then we need to use the network to control the timing. So you can broadcast commands to tell everybody what to do. You can tell them in advance at a certain time, I want something for you to do. You can hand shape commands for them. And so Alon, who invented Core XY and then started Shaper Tools, did a thesis on, let's see, did a thesis on virtual machine control. My student Jake picked that up on data flow machines. This is a video of him making network machines where you just make a software controller and use that to coordinate all the motion of it. And that was used, for example, in, let's see, and I'll link this because it's very relevant for today's class. This was a 3D printer Jake made, and you should recognize now Core XY, the belts, the framing. But what he's doing here is this is a printer that measures the forces and flows, sends the data back, and then he trains a model so the printer learns how to print a material it's never seen before. It can print a recycled or renewable material. And so to do this, the machine is just a real-time network. And with a traditional 3D printer, you just throw the file at it. Here, you send commands to the machine. It's sending you back a lot of data on what it's doing. And then you use that to learn the settings to print the unfamiliar material. And so that's a good example of network machines. So then you're going to talk to the machine. Most common commands are G codes, which are ancient, long past their due date, but still common. And then a common way to handle them is interpreters. So this is a common platform where it takes G codes in and then controls stepper motors. And so that's a classic version of it. It's handy, it's convenient. This one board, you connect your motors and send your G code. On the other hand, you have to map the G code commands into what your machine does. And it looks very different if you have a Delta bot or a Core XY. And then there's no scalability. If you need one more motor, you're out of luck. That's what the board can do. So they're commonly used for standard solutions, but they're not flexible. You need to build a user interface to the machine. And so this chili pepper is a really nice project for sending G codes. And it does all the different tasks of, let's see, Let me link. A chili pepper is one. Another one is UGS. Another one is candle. And UGS is primarily what I use. What these do is everything for this purpose. Yeah, another one is CNCJS. Another one is candle. Um, they visualize your G code. They show you the G code. They let you edit the G code. And they also give a real-time interface that let you jog the machine and set 0 on the machine. So those are all examples of building a user interface to the machine. Then you need to plan the paths. So you might have used mods to machine. If we go through all the steps now in this, this reads an image in, this adds tabs, this finds the distance of the edges, this offsets for the tool diameter, this finds the edges, this turns them into vectors, then this sends it back to the coordinator, then the coordinator accumulates those, this converts it to a G code, and then this sends it to the machine. And each of these you can open to see what's going on. So this shows you how the G code gets interpreted. And so I originally wrote mods, so rather than all of that being hidden, you can see the steps that go into it. So you need to figure out the path for the machine. You need to figure out how you're going to represent designs on the machine. And then finally, this last group of links, these are vendors one level up. So they provide not just mechanisms, but they provide mechanisms and motors and controllers and everything you need to make finished machines. These are vendors just for the motors. And again, thanks to our friends in Shenzhen, the cost of these have come way down. And let's see, I didn't, yeah, no, I mentioned, I'll say what I just interrupted myself. The cost has come way down, and it's actually easy to customize these. You can get a motor made with custom fittings, for example. And then you can decide, do you want a stepper motor, a servo motor? Remember, motors have a torque where they're most efficient. A geared motor has the reduction built right into it. So those are much more convenient to buy now. Then these are all standard solutions for controlling the motor. So Pololu is a vendor that has lots of motor controllers. These are all uh, um, these are all vendors that have. Okay, I'll fix those links. These are all standard solutions for the controllers. So you can make your own from scratch. These are standard solutions for controllers. Then these are just a few different of many different versions of open stepper controllers. Then next comes Arumbu is a project I did that started at an instructor boot camp in Kerala. And I wanted to see how much we could simplify the machine. And so an example of using that is this project from Yanni. This is a little 3D printer. And in Arumbu, what we're doing is every degree of freedom in the machine is plugged into USB. And then actually, yeah, sorry, let's go back to the Arumbu project. And let's go to serial step and then down here. So right now I'm controlling The tones you hear are the stepping rate. Here, instead of a central controller, each motor gets connected to a USB port and then have a USB hub. USB 3 will give you about an amp per port, which is enough for motors of this size for things like 3D printer and tabletop milling machines. Let's see, Sahin is putting a couple examples of Arumbu projects into, nice, into the chat. And so what this does is it gets rid of all of the embedded code. All the motor knows how to do is get a step in a packet, and then in software over these USB ports, you coordinate the motion. Modular Things is a system built by my former student, Jake, working with Quentin and others, that does a little bit more, that it's based on real-time networks, but adds a little more complexity to the nodes so you can give higher level commands to them rather than just simple steps. And so that's a kit for the modular things. This is a link of lots of open machines for Fab Labs you can make in Fab Labs. I had shown you Quentin's Arumbot. I'd linked Yanni Sampo. Clank is machines Jake is making with the modular things. Jubilee is one from a former student, Nadia, of her modular machine with tool changing. Jens has a whole family of the Felleswerkstätte machines. Danielle has led with the Open Lab Starter Kit, which is a complete Fab Lab of open machines. And then a lot of machine companies have spun off. So Elan started Shaper Tools, for example. Nadia started, spun off what became Open Machine and then became Banham Tools. Ultimaker started Fab Lab in the Netherlands. Form Labs started from students from my lab. Those are examples of commercial companies based on the machine building. These last two are fun one. Joseph makes sloppy bad machines that don't work well. And Simone is another really interesting machine builder who has she initially made bad machines and then decided she wanted to make good, not bad machines. But this is just interesting people for machine building doesn't have to be serious. Ferdy? Hand
Yes,
raised,
hello.
Ferdy?
Yes, hello. Sorry, I just wanted to repeat my question on the model identification, system identification algorithm I posted. Is it okay for now, or don't we have time for that?
You mean the model predictive control? Oh,
Yeah,
yeah,
like exactly how.
yeah. For this week, I doubt you'll do it. The model predictive control is advanced machine building. It's good to know it's there. And the way you know you need it is if your machine shakes, if your machine is noisy, if your machine settings drift, those are all signs you need to be doing model predictive control. You don't need to do it to start.
Okay.
Yep. Okay, so you're going to design a machine, you're going to then automate it. And for this week, you need to divide into teams. So like one team can be mechanism, one can be motor control, one can be end effector, one could be user interface. For this week, everybody doesn't need to do everything. You can segregate with clearly defined jobs. Make a group page for your machine. On your individual page, we want to know what you did for the group project. And then in 2 weeks, when we rejoin, we want to see everybody's machine. So we're going to go to this page. For each lab, you should have a lab page. On your lab page, I want you to prominently place your machine link. Put a demo video, show it live if you can, but for posterity and backup, put a demo video. And then these are short. We can spend about a minute per lab, and we're going to go around the world and see everybody's machine. the real goal of this isn't to make spectacular machines in a 2-week assignment, but it's for you to learn all the steps from mechanisms to power electronics, all the way up to the applications, to see all the things come together and to inspire you and make something big. You learned you can make your own furniture. This week, you learn you can make your own machines. And you can think about machines that fill degrees of freedom that you wish you had in your lab, but you don't have. So after this, Monday recitation, open Saturday time. Over the next 2 weeks, students, local and global instructors meet to review everything. And the goal is at the end of this 2-week stretch, you've done the machine assignment, and don't go crazy. We want to see a neat machine, but you could swamp yourself just with that. We want you to also use this time to get caught up. Coming out of this midterm, we want you caught up on all of the preceding assignments. So what's left is the few remaining assignments and then the final project. And we need all of that for you to stay on schedule. Okay, I'm eager to see your machines. This is always creative and a lot of frustrating and then a lot of fun. When it was exciting the first time you blinked an LED, it's exciting the first time you made a motor spin. When you finally make your machine move, it's really, really exciting. So I'll see you for the recitation, and then I'll see your machines in 2 weeks. Have a good break. Bye-bye.
Bye-bye.
Bye.
Please call up.
Dismiss all.
Bye, thanks.
Bye.
おやすみなさい。